Today we will see how to evaluate the integrals of the form 1 over ax squared plus bx plus c dx. These integrals are extremely important. All the Calculus 1 students are required to know how to evaluate the integrals of this form. These kinds of integrals can be divided into three groups based on the nature of the quadratic form in the denominator. The quadratic form can be classified into three groups based on the discriminant. What's a discriminant? Discriminant is usually given by delta, which is defined as b squared minus 4ac. If your b squared minus 4ac, or this delta, is greater than 0, then we have one approach. If delta is equal to 0, then we have another approach, and if delta is less than 0, we have a completely different approach. So what are those three approaches? For delta greater than 0, we can factor the denominator. We can factor the denominator, and afterwards we can go for the partial fractions. For the other two cases, where delta equals 0 and delta less than 0, we have two other approaches. If your delta is equal to 0, then again we can write the denominator as a complete square. And then you can integrate it using the result in the standard table for integration ax plus b raised to the nth power dx. If delta is less than 0, in that case, once again we need to complete the square, but it will not be a complete square alone. It will also have another numerical value added, a positive numerical value added. In that case, you will have to go for the tangent theta substitution. Or in other words, the final answer will be of the form tangent inverse a function. We will look at an example from each case. So here's the first situation. Delta is greater than 0. Once again, delta was defined as b squared minus 4ac, and delta is greater than 0 means I can write down an example like this. Integration 1 over 2x squared minus 7x plus 3 dx. Now if you look at the delta in this case, which is defined as b squared minus 4ac, you can see b is equal to negative 7. So it will be negative 7 squared minus 4, a is equal to 2, and c is equal to 3. If you simplify this, you get 49 minus 24, which is positive. That means I can factor this out, and then we can go for the partial fractions. Alright, so first we will factor this out. If you factor 1 over 2x squared minus 7x plus 3, we can write it as 1 over 2x minus 1 times x minus 3. That's simple college algebra, which is a requirement for calculus class. So I will not help you on factoring this polynomial. I hope you know it already. And then what we have to do is to see the partial fractions. We know we need to split this into partial fractions as a over 2x minus 1 plus b over x minus 3. Now finding values of a and b is going to be very easy. We have seen a nice shortcut that works very well in these kinds of situations. What is that shortcut? We look at the denominator of a, which is 2x minus 1. Then that same denominator should be closed down from the denominator of the original function. We know that this denominator will be equal to 0 when x is equal to 1/2. We replace that value in the rest of this on the left hand side. So if you put 1/2 for x, we get 1 over 1/2 minus 3. Now we need to simplify that. 1 over 1/2 minus 3, if you simplify that, it becomes 1 over negative 5/2, which is equal to negative 2/5. So that's our answer for a. A equals negative 2/5. The same way we can find b. In order to find b, we need to look at this denominator. We need to close down that same term from the original function. We know that this term right here will become 0 when x is equal to 3. Then we put 3 in the rest of this function. It will be 1 over 2 times 3 minus 1. which means we have 1 over 5. Therefore, b equals 1/5. Alright, now we have split that into partial fractions. Now we can easily integrate this question. Integration 1 over 2x squared minus 7x plus 3 dx. We split that into partial fractions as negative 2/5 integration 1 over 2x minus 1 dx, and I have 1/5 integration 1 over x minus 3 dx. Alright, now what? We have a fantastic theorem to be used in such cases as well. If I have to integrate something like f prime x over fx dx, where f prime x is the first derivative of fx, which is the function in the denominator, we know this answer is equal to natural logarithm absolute value f of x. Of course, f of x cannot be equal to 0. I have proved this theorem in the past. I'll have the link posted down below in the description for those who are interested in the proof of this theorem. So in this video, I'm not planning to prove this theorem. Instead, I'm going to straight away use the theorem to evaluate these integrals. Alright, now look at this first term. If you look at the first term, we can see that it's 1 over 2x minus 1. If I differentiate 2x minus 1, I need a 2 on the numerator in order to apply this theorem right here. But I can easily create a 2. In order to create a 2, I simply have to push this one inside the integral. Let's do that. I'm going to rewrite this integration as negative 1/5 integration 2 over 2x minus 1 dx. The other integral is 1/5 integration 1 over x minus 3 dx. I know very clearly that if I differentiate x minus 3, I get 1. Therefore, I can straight away apply this theorem for that second integral. So let's go ahead and evaluate this complete integration. The first term is negative 1/5, and that should be natural logarithm of the denominator. Natural logarithm, the denominator is 2x minus 1. And the other one is 1/5 natural logarithm, the denominator, which is x minus 3. Remember to write them inside the absolute signs. This is an indefinite integral, therefore to complete this answer, we will need to add an arbitrary constant plus c. Alright, we are done with that example. Now we will look at an example for the second case. The second case is when delta is equal to 0. Remember, delta was defined as b squared minus 4ac. When this is equal to 0, we said we can write the denominator as a complete square. So let's look at an example. Let's say we need to evaluate the integral 1 over x squared minus 6x plus 9 dx. Now in this case, we can see that b squared minus 4ac, not that a equals 1, b equals negative 6, and c equals 9. So b squared minus 4ac will be equal to negative 6 squared minus 4. A is 1, c is 9. So if I simplify all that, I get 36 minus 36, which is equal to 0. Alright, therefore we can write this denominator right here as a complete square. Let's go ahead and solve this problem. I'm going to write down this integration as integration 1 over, we know if you factor that, it's going to be x minus 3 everything squared dx. Once again, I will not help you finding these factors. That's from college algebra. You should know it before you enroll in calculus class. Alright, now we are going to use the integration ax plus b raised to the nth power dx result from the standard table. We know that this integral is going to be equal to ax plus b raised to the n plus 1 all divided by a times n plus 1. This cannot be used if n is equal to negative 1. But in this our example, n is not equal to negative 1, because we can rewrite this given integral if necessary as integration x minus 3 raised to the negative second power dx. In that case, our n is equal to negative 2, not negative 1. Therefore, I can go ahead and use the result right here. So let's go ahead and do that. Then I will get ax plus b which is just x minus 3 in this case, raised to the n plus 1. N is equal to negative 2. Therefore, this has to be raised to the power negative 2 plus 1, which is negative 1, divided by a times n plus 1. A is equal to 1. So it's going to be 1 times negative 1, all divided by negative 1 therefore. And there will be a plus c because we are evaluating an indefinite integral. We can write this answer somewhat better as negative 1 over x minus 3 plus c. Alright, we completed that example as well. The last case we have is when delta is less than 0. Once again, please don't forget that delta was defined as b squared minus 4ac. Alright, let's look at an example. Let's say I need to evaluate the integral dx over x squared minus 4x plus 13. Now in this case, we can see that a equals 1, b equals negative 4, and c equals 13. So if I solve for delta, which is b squared minus 4ac, I will have negative 4 squared minus 4 times a is 1, c is 13. So if you simplify that, we get 16 minus 26 times 2, which is 52. And that's very clearly negative. So when you have it as negative, we will happen to use the tangent theta substitution. Before doing that, we will have to process this thing a little bit. We need to write it as a complete square plus a positive constant. So let's do that first. I'm going to write this integral as dx over x minus 2 everything squared plus 9. That's how we will complete the square. Once again, I'm not going to explain you how to complete the square of a quadratic form. You are expected to know it from college algebra. Alright, now we need to see that this integral can be written as integration 1 over x minus 2 squared plus 3 squared dx. Well, I wrote this as 1 over something and then dx outside. That is just to avoid any confusions of writing it this way. For some students, they ask, can you write it like that, or can you write it like 1 right here and dx out there? Well, both formats are exactly the same thing. You may do it in whatever the way that you like. Alright, now once you process your integration like this, we can then go for the substitution. So what's the substitution you need? We look at this term right here, x minus 2 everything squared. We're going to substitute that x minus 2 being equal to, we look at this term as well, that's a 3 squared. We're going to use that 3. We're going to substitute x minus 2 to be equal to 3 tangent theta. When you do that, we get dx being equal to 3 secant squared theta d theta. Alright, let's write down this integration equal to integration 1 over x minus 2 squared. X minus 2 is equal to 3 tangent theta. Therefore, x minus 2 squared should be equal to 3 tangent theta everything squared, which we can write as 3 squared tangent squared theta. And then we have plus 3 squared. And then we have this dx term. The dx term is equal to 3 secant squared theta d theta. So let me write it as that. 3 secant squared theta d theta. Alright, now we can do some simplifications. From the denominator, we can factor out 3 squared. Therefore, I'm going to write down that 3 squared in the bottom. 1 over 3 squared integration 1 over tangent squared theta plus 1. And then on the numerator also I have a 3 which can also be factored out. Therefore, I'm going to write that 3 also outside. And I have a secant squared theta d theta. Alright, now we can do some nice simplifications. Right here in the denominator I have a 3 squared, and right here I have a first order 3, therefore I can cancel off one of those 3's. And then in the bottom right here we have tangent squared theta plus 1, which is equal to secant squared theta from the second of the 3 Pythagorean identities from trig. Therefore, I'm going to go ahead and cancel off all of this with secant squared theta term. Alright, now this has become equal to a third integration just 1 d theta. Therefore, this becomes a third theta plus c, which is a third theta. In order to find theta, I need to go back and look at this substitution right here. From that substitution, we can see that tangent theta should be equal to x minus 2 divided by 3. Therefore, your theta should be equal to tangent inverse x minus 2 over 3. Therefore, this is equal to 1/3 tangent inverse x minus 2 over 3 plus c. Alright, that's the answer for that example. Alright, now if you would like to practice these methods, I would like to give you 3 homework questions. Here's your first question. Evaluate the integral 1 over x squared minus 9x plus 20 dx. The second question is evaluate the integral 1 over 9x squared minus 12x plus 4 dx. The third question is evaluate the integral 1 over x squared plus 10x plus 34 dx. Alright, see if you can obtain the answers for these questions. If you need any help, please feel free to let me know. Alright, I hope you enjoyed this video. Thank you so much.